Hi, welcome back. Today we're looking at how to factor more quadratic expressions. What do I mean by more? Well, previously we learned how to factor x squared plus bx plus c, and here the coefficient in front of the x squared was always a 1. So that's sort of a special case. We want to go more general. We want to look at this version here now today, where this coefficient a could be, any kind of integer really. And so that's what we're trying to get to. Let's quickly review how we factor expressions of this case first, right? This special case first. All right, so what we said was we can factor this into essentially two binomial products, right? There'll be some kind of x plus something times an x plus something. We call this x plus r and x plus s, okay? So if you take these two factors and you FOIL them together, then what we'll get is some kind of x squared plus some kind of r plus s times x plus r times s, right? That's the natural result of what you get when you FOIL these two binomials together. And so comparing this expression to sort of the original one, we can see that what we get for b is going to be equal to r plus s, and c would be equal to r times s, right? So essentially, to use this knowledge to help us factor quadratic expressions, we have to recognize that c would be broken up into two factors, r and s, and then if you take these two factors of c and add them together, you'll get b, right? So let's try an example here. Let's try looking at this one right here. Okay, so it's x squared plus 6x plus 8. So the key is we recognize that we need to find two factors of 8 that add up to give us 6. Okay, and we can make a little table here. So basically we need factors of 8 that add up to give us 6. Okay, this is essentially what we're trying to do. So what are possible factors of 8? Well, you could have 1 multiplied by 8, right? That's a pair of factors. Or you could have 2 multiplied by 4. That also works. 3, nothing. 4 times 2 works, but that's kind of this just repeated, right? And same thing with 8 times 1. That's the same thing repeated here. So we check 8 plus 1. Does that equal 6? No, it does not. 2 plus 4. Does that equal 6? Yes, it does. Okay, and so this must be the pair of numbers r and s that will produce the factored form of our original expression. So the idea is we must be able to write this down as some x plus 2 times an x plus 4. That's the proposal. If we FOIL it out, we can check, right? We're going to get an x squared plus a 4x plus a 2x plus 2 times 4 is 8. And if we simplify that, we get x squared plus 6x plus 8. Sure enough, it works. Okay, this is exactly what we're looking for. And so yes, this is going to be the factored form of our original expression here. That's the method that we looked at in our previous class. Now today, we're going to imagine that this a doesn't have to be the number 1. It can be any integer. And if that's true, how do we factor something now of this form? So the idea here is we're going to follow the same kind of pattern as before. We're going to split this expression up into the product of two binomial factors, x plus something and x plus something. And just like before, we'll call this second term our r and our s, but the first term here we will call p. Let me do that in a different color, P and Q. Okay, so previously we had assumed that these are going to be 1s because when you multiply them together, 1 times 1 just gives you a 1x squared. And for this special case, we're only dealing with an x squared as our first term of that polynomial. But here we have an ax squared where this is not 1. And so we cannot assume that P and Q here are 1. They could be anything. All right, so let's FOIL this out and let's see what we get when we FOIL these two factors together. Well, we're going to FOIL, right? So let's look at first times first, outer times outer, inner times inner, and then last times last. Okay, we're gonna use our FOIL technique here. So the first terms, PQ times PX times QX, what's that going to give us? That's going to give us PQX squared. Now outer times outer, that's px times s. Well, that's going to give us psx. Inner times inner, that's going to give us qrx. And finally, last times last, that's just going to give us r S. Okay, so this is the idea. Let me color these in blue. This one's also blue. And this one's also blue. These are going to be green. This is green, and that one's green too. Okay, so that's the idea. Oh, looks like I missed this part here. Green. Okay, so this is what you get when you FOIL this out. Now notice what we're getting here. This first term, this pqx squared, corresponds to this ax squared. The c corresponds to this rs, but this bx, this middle term, actually corresponds to the sum of these two. So I want to sort of look at these two combined together as yielding that middle term, that bx. And so if we do that, we can essentially sort of take this, let's take it like this, and let's try and simplify it, right? So this middle term then is actually going to simplify down into some kind of ps plus qr multiplied by x. So we can move this over here. Okay, so this becomes the simplified version of what we're doing. And when you write it down this way, it's very easy to see then that a is going to equal p times q. In fact, let me just, a is going to equal this p times q. B is going to equal, well, this sum of stuff right here. Let me grab that. And finally, C is going to equal this R times S. Okay, that's the idea here. So let's just highlight that. This is the key. This is the key to how we're able to understand how to factor this ax squared plus bx plus c, right? We can express the a as the sort of the product of these two factors, p and q, and we can express c as the product of these two factors, r and s, and then b is some like combination of all of those right there, all of those factors. So how does this help us? Well, there's a few different methods we're going to use when we factor quadratic expressions in general. Today, what we're going to focus on is this a term and this c term, okay? Because it's relatively simple to see that the product of this p and q are going to give me a, and the product of this r and s are going to give me c. So let me give you an example here. Let's look at, how about this example here? Okay, so let's say we have some 2x squared plus 5x plus 3, right? The whole idea here is that for the first term here, this is going to be produced from the product of the first times the first, right? So that's what we have here, the first times the first, and we need to find the factors of this number here, 2. What are the factors of 2? Well, really, it's going to be 1 times 2, right? That's pretty much it. Okay, so that's the factors of the that we're going to get for our first terms, and for the last term here. What are the factors of 3? Well, that's really just going to be 1 times 3, isn't it, right? And so these are potentially, if we can actually factor this quadratic expression, these are potentially going to be the values we use for p, q, r, and s. All right, so let's try it out. Let's try using this. So remember, these are the first terms, right? So what I'm saying is this should equal some kind of product, and it's going to be 1x. And then over here, we'll have a 2x, okay? So that's what this represents, the 1 and the 2. And then over here, well, this should be x plus 1, and then this will be a 2x plus 3, okay? So this is x plus 1 and 2x plus 3, okay? So let's FOIL this out. Let's see what we get. We're going to get a 2x squared, and then plus something, and then over here we'll get a 3 times 1, which is a 3. Now in the middle, it's going to be outer times outer, so that's a 3x, and then inner times inner, that's a 2x, but I just want to add these together, 2x plus 3x, this is 5x, okay, so 5x, and is this what we were looking for? Yes, it is. So this method does in fact work. This is going to be the factored form of this sort of more general quadratic expression here, where this initial term is a 2, it's not a 1, okay? So this method appears to work. Let's develop it a little bit further. So what I've got here is another two examples where we're factoring some general quadratic expression where this initial term is not 1, okay? So let's try it out, okay? So just like before, the whole idea was we wanted to find what are the first terms of this sort of binomial product going to be, right? We have some x plus something, we're going to have some x plus something, but what are these first terms going to be? Okay, so the first terms should be the factors of 5. Okay, so what are the factors of 5? Well, we have 1 and 5 is a prime number, so that's pretty much it. And then the last terms, right, should be products of 2 or factors of 2. So what do we have there? Well, 1 and 2. I think 2 is a prime number as well. That's all we have. Okay, so let's try it out. We're saying this should be a 1x, this should be a 5x, this should be a plus 1, and this should be a plus 2. Okay, let's FOIL this. Let's see what we get here. So x plus times 5x will give us our 5x squared. That's good. Our last times the last will give us a 2. Okay, so far everything is matching. In the middle then we're going to get a 5x plus a 2x, which is a 7x. And yeah, that's exactly what we're looking for. So guess what? That does actually work. Okay, so our method appears to have value. Just find the factors of this A and the factors of this C, and then use them to construct your two binomial factors here. Okay, so let's try the next one now. Okay, same idea. This should equal to some x plus something times some x plus something, but we need to figure out what numbers we're going to put over here, our PQRS, right? So once again, let's look at the first terms, and we'll have the last terms as well. We need to figure out what are the factors of 3. Well, the factors of 3 are 1 times 3, right? That's it. 3 is a prime number. 5 is also a prime number, so just 1 times 5, and that should be it. Okay, let's try it out. So we're going to have the first terms are 1 and 3, and the last terms are 1 and 5. Okay, let's FOIL it together. Of course, x times 3x will give us our 3x squared. And at the end here, our 1 times 5 will give us a 5. So far, so good. Now, what about the middle? Well, outer times outer, we're going to get a 5x plus a 3x, and altogether that gives us an 8x. And look at that. This does not work, okay? It doesn't work. What's the problem? What happened? Well, it turns out there is another way we can factor 5 and 3. What I mean is, over here, we wrote down 5 as 1 times 5, and that's true. But 1 times 5 is also can be sort of flipped around, and you can think of this as 5 times 1. 5 times 1 is also 5. Right, isn't it? So what we can do is we can imagine we have a combination of these two as our first coefficients here, and these two as our last. But we could also flip that around on the last, so you could get another set of factors here, another combination essentially, that could maybe give us a different answer. So let's see what we would get there. So if we try this second combination, well, the first and the first are the same. So this is still 1x and 3x. But now we're going to have plus 5 here, and we're going to have plus 1 here. Okay, so it's a little bit different, right? So notice this is going here, and this is going here. Okay, so let's FOIL this together. Again, we get a 3x squared for our first term, and our last term is still 5. That doesn't change, but in the middle, here we're going to get a 15x plus a 1x. Well, that gives us a 16x, and this is actually what we are looking for. So this is the factored form that we want, and we get this because we discover actually there's sort of hidden inside here another combination that we can use based on the factors of 5 and 3. You have to sort of flip that one around to get another combination. Now you might ask, let me write this down like this. Well, you get 1 times 3 times a 5 times 1. What if we were to flip this around again as well? So could we unlock yet another combination is the question. If we did 3 times 1 and then 5 times 1 here, right? Does this constitute another combination? So let's write it down. What do we get here? So our first terms are going to be 3x and 1x, and then our last terms will be a 5 and a 1. And so if you look at this carefully, notice we have a 3x plus 5, and here we have a 3x plus 5 multiplied by an x plus 1 multiplied by an x plus 1. We have actually replicated the very first combination that we tried. So it turns out that if you do sort of a double flip, you flip both the first and the last factors, you do not get another unique combination. You are going to repeat. Okay, so flipping twice does not give you a new combination. All right, so we're not going to do that. Flipping once, maybe just the last factors, that will unlock a new combination. Okay, so just keep that in mind. It's a good way to sort of prevent you from double counting or trying extra combinations here. But that's sort of the process that we're going to use for this method. It's a little bit of trial and error, right? We're going to discover and unlock combinations that potentially could work based on the factors of A and C. And by trying these combinations together, trial and error, we'll eventually, hopefully, stumble upon the correct combination of binomial factors that give us exactly what we're looking for in our original expression, right? It's this middle term that it's kind of what we're trying to find. All right, so let's keep going. Now, these two examples are going to start to get a little bit more interesting, and we're going to unlock sort of more combinations that we can try out. I'll show you how that works. So once again, we're looking at sort of the two first terms and we're looking at the two last terms here, right? So the first terms are going to be based off of the factors of, the factors of 5 here, right? So what are the factors of 5? Well, we have 1 times 5. 5 is a prime number. That's pretty much it. Now 6 is not a prime number. So we do have 1 times 6, but we also have 2 times 3, all right? And so we have 2 possible factors here, but then in addition to that, just remember what we did, we can flip these around to unlock more combinations. So we can also have 6 times 1 and 3 times 2. And so for each of these, we're going to have as our first terms 1 times 5. And so this is going to give us essentially 4 separate combinations for us to try out to see if we can unlock this 17x as the middle term. Okay, so let's try these out, okay? What I'm saying is let's go one by one and see if we get that original expression. Okay, so here we're going to have 2 factors, and the first is going to be 1 and 5. So this should be 1x and 5x. Last will be 1 and 6, so 1 plus 6. Okay, if we FOIL this out, what are we going to get? Well, we're going to get a 5x squared plus something plus 6, right? So the first and the last, that's pretty good. The middle terms, well, here we're going to get a 6x, and here we get a 5x. Add that together, you get 11x. Is that what we want? No, we want 17. So this doesn't work. Okay, let's try the next pair. We're again get an x and a 5x, and then here we're going to get a 2 and a 3. Okay, so once again we get a 5x squared and a 6 over here, but in the middle we're going to get, here's a 3x plus a 10x. That's going to give us a 13x. Once again, not what we want. Okay, let's try again. We're going to get x and 5x, and here we'll get plus 6 and plus 1. Hopefully this one's it. 5x squared plus 6, and in the middle we're going to get a 1x plus a 5 times 6 is 30. So this is actually a 31x. That is too big. Okay, we have one more shot. If this doesn't work, then that means we actually cannot factor this this way. Again, we'll get an x and a 5x, and here we have a plus 3 and a plus 2. So just like before, the first and last terms are guaranteed to be correct, but that middle one is the key. Here we have a 15x plus a 2x. That's going to give us a 17x. And yeah, finally, we did get what we're looking for. So this is going to be the answer here. This is the factored form of our original expression. Okay, so you unlock combinations, and you just have to be conscious of sort of how these combinations are being created. Now, when we look at the next example, notice that this quadratic and this quadratic are like the same, except that here we have a negative sign, where here we had a positive sign. So what is that going to do for us? Well, the factors of 5 and the factors of 6 are going to be exactly what we had here, right? So this is going to be exactly the same. But then how does that work? Because here we can see all of these middle terms were positive because all of these numbers that we're multiplying together are positive. So how can you get a negative middle term over here using these factors? Well, you can't. However, notice that although 1 times 6 equals 6, negative 1 times negative 6 also equals 6. And so really what we have to do here is we have to multiply all of these factors here sort of by negative 1. So we have to negate everything, and this unlocks a whole new set of possible combinations for us to use, right? And because we already know it's going to be the 3 and the 2 that gives us the 17, putting a negative 3 and a negative 2 would give us a negative 17, right? So our answer here, our factored form should be x minus 3 times x minus 2, right? It should just be from this combination here, and we can test it, right? We'll get an x. Oh, what are we missing? We're missing a 5. We're missing a 5 over here. So this should give us a 5x squared, and then this will give us over here a negative times a negative is going to give us a positive. So this is a positive 6, but in the middle, notice this is going to be a negative 15x, and this will give us a negative 2, giving us a total of a negative 17x, which is exactly what we expected. Okay, so there we go. This is going to be the factored form here. So just like when we were doing the special case where a was equal to 1, whenever you have a positive value for c, you know that both of the factors here are going to have the same sign. They're either both going to be positive or they're both going to be negative. And what determines the sign of these numbers here, of these terms, is going to be the sign of b. If b is positive, then both of these terms are going to be positive. And if b is negative, then both of these terms are going to be negative. Okay, so that's sort of the idea here of how we can solve problems like this. Let's look at some more. Now with this expression here, notice that there's going to be a negative value here for c. That will affect how we deal with these kinds of problems. Okay, so again, we're going to try and find sort of the factors we're going to use for the first term and the factors we're going to use for the last term of our two binomial factors. So let's look at this first. We're looking at the 5. Well, the factors of 5 is a prime number. So it's going to be 1 times 5, right? And for 6, we're going to get 2 times 3, well, 1 times 6, and also 2 times 3. But this is a negative 6. So that means one of these numbers has to be negative and one has to be positive, because the product of a positive and negative will give us a negative. So we know that these factors must have opposite signs. But we don't know if the 1 is negative or if the 6 is negative. All we know is that one of them is, okay? And so let's just assume the first one is negative here, okay? So this is going to give us sort of the possible combinations we have to look at. But of course, remember, you could flip these, right? So if we flip them, we're going to get a combination here of 6 times negative 1 and a 3 times a negative 2. So that's another option. And then maybe we were wrong about having the negative on the 1 and the positive on the 6. Maybe this is wrong. So we have to do the other possibility and multiply everything by negative 1, basically negate it. So that's going to give us options of 1 times negative 6, 2 times negative 3, negative 6 times 1, and negative 3 times 2. And so this unlocks even more combinations for us to try. And of course, all of these are going to have the same 1 times 5 as the factors we're using over here. Okay, so let's grab all of these. There we go. All right, so there we go. Here we have it. 8 total possible combinations for us to try and figure out what the correct one is that's going to give us this positive 13x here as the middle term. Okay, so that's a lot of trial and error, but there is a pattern here, and we can make it a little bit faster to go through these. Let's just sort of look at what this pattern is going to be. Okay, so for this very first one, let's just look at this very first one. Okay, what we're saying is this should be a product of two binomials, and the first term should be 1 and 5. Okay, so we're going to have 1x and 5x for the first terms, and then the last term should be -1 and +6. Okay, so let's FOIL this out. Let's see what we get. Going to get a 5x squared plus, well, let's do outer times outer. That's going to be a 6x. And then we're going to have a -5x. And then we're going to get a -6, right? Okay, so that's sort of what we get here. Now, I want you to notice the pattern. Now, of course, 6 and -5, this is actually going to simplify to just x, right? 1x. So it's going to simplify to 5x squared plus x minus 6, which is not what we want, okay? It is clear that this 1x is not 13x, okay? But more important, I want you to look at the pattern here. The pattern here is, let's draw this as a 1, okay? Let me draw it as a green 1, okay? This is 1, and this 5, let me also make that as green. Actually, you know what? Let me make this as blue. Okay, let's do this as blue. And then we'll make this one also, well, it's a -1. Okay, let's make this one blue. And let's make this 6. Okay, now why am I doing that? This outer term is what we have here as blue. This is the other outer term also as blue. This is the inner term as sorry, those were green, and these inner terms are blue. Okay, so I'm just trying to color code this so you can see what's going on, right? And then over here, the important point is that this 6, this comes from the outer times the outer. So I'm going to color this green, and this -5, that comes from the two inner terms multiplied together, okay? And so essentially here, we actually don't have to write out this entire thing to try and figure out what the middle term is going to be, because that's the key. The first term is always going to be a 5, because 1 times 5 is always going to give us a 5. So at every single combination that we try, we never have to worry about not getting a 5x squared here. We will always get a 5. And same thing for the last term, right? All of these last term factors are guaranteed to give us a -6. That's how we derive them. So we never have to worry about the last term. We only have to worry about this middle term, and that comes from the sum of the outer times the outer and the inner times the inner. This 6 and this -5, that's the key. And so what I want to do here is I just want to focus on those middle terms. Let me put a line here, and we'll make another line here. And you know what, maybe let's give ourselves a little bit more room. Stretch this out a little bit. Perfect. Okay, so what I want to do is I want to think of this as FOIL, right? I want to find the combination we get for the outer times the outer and the inner times the inner. Okay, so when we do this, we see the outer times the outer is going to give us our 6, and the inner times the inner is going to give us our -5. And when we add those together, we're just going to get 1. Okay, and so this is the number we're actually concerned about. This is the middle term we have to compare to the original expression. So instead of writing all of this stuff out, I'm just going to work within this table here. So once again, over here, outer times outer is going to give us a 3. Inner times inner is going to give us a -10. So this gives us a +7. Oh, sorry, this gives us a -7. -7 is not 13, so we keep going. Here we get outer times outer, -1 times 1 is -1. 5 times 3 is going to give us a 30. This gives us 29. 29 is not 13. Okay, so let's keep going. 1 times -2, this is a -2. 5 times 3 is a 15, so this is going to be a 13. Oh, look at that. That's exactly what we were looking for. Okay, so this here should be the correct combination. Okay, we just need to check the middle term to see if we get a 13 here. Okay, so what I'm saying is that the correct factorization should be, first times first, going to be x and 5x. And then the last term should be a 3, and a negative 2. That's what I think it should be. Let's double check. Okay, x times 5x is going to give us a 5x squared. Outer times outer give us a minus 2x. Here we'll have a plus 15x, and then we'll get a negative 6. And when we simplify, this is 5x squared plus 13x minus 6. Yeah, that's what we want. We got it. Okay, so a lot of potential combinations to cycle through, but you can do it. And doing it this way by just focusing on the just focusing on this middle term, that's going to be a faster way for you to sort of grind through each of these potential combinations. All right, so that's the idea. I want to show you one last example to illustrate potentially the pitfalls of this method. Here's the last example I want to look at, and it looks innocent enough, but it's actually not going to be so innocent. So let's take a look at this. Once again, we kind of want to find what the factors for the first term will be, and then we'll have our middle terms that give us our b, and then our last term over here. So you can sort of set up a chart if you want to, just like this. And let's look at the factors of 8 that are going to give us our potential first terms. Okay, what do we have? We have 1 times 8, and of course we have 2 times 4, and I think that's it. Now for the last term, we have a negative 15. Okay, so again, this is a negative. Keep that in mind. So we could have a negative 1 times a 15, or we could have a negative 3 times a 5. And I think that's pretty much it, okay? However, we have to imagine all of the other potential combinations here. Okay, so let me take this 2 times 4 and let me move that down because we're just concerned with all the combinations of 1 times 8 first, right? We could flip these, okay? We could flip these around. We'll get a 15 times a negative 1. We'll get a 5 times a negative 3, okay? So that's one way that duplicates our possible combinations, is flipping these two on the last, for the last term. And then because this is negative, we don't know if it should be on the negative 1 or on the 15. So we have to duplicate all of these again, but negate them. And so what we could have then is a 1 times a negative 15, a 3 times a negative 5, a negative 15 times a 1, and a negative 5 times a 3. All right, so look at why this is not so innocent, because now what we have to do is we have to duplicate all of these again and try them with potentially 2 times 4 as the first terms. Okay, so we literally have to take all of these, duplicate them again, and try them with 2 times 4. Okay, that's, let me just put this down here as a reminder of what we have to do here. But yeah, these are a lot of combinations, right? We're going to have to try all of these. And let me duplicate this again. And one more time, right? So this is what we're getting, right? We have 8 possible combinations where the first terms are 1 and 8, but we have another 8 when they're 2 times 4. That's going to give us a total of 16 possible combinations for us to work through. That is a lot of combinations. And you know what? I'm not even going to bother to go through this. I just wanted to show you sort of the problem that you can get is that you can potentially get a lot of combinations here, all right? In fact, how did we get to this 16? Where did that come from? Let's think about it. Okay, so for our A value, we had 8, right? That's what we have here. And for C, we had negative 15, okay? So when we looked at these two, we created our possible factorizations of 1 and 8 and 2 and 4, right? And over here, you basically had 1 and 15 and 3 and 5, right? But one of these numbers was going to be negative, okay? So this is sort of the idea. If you think about it this way, you sort of had 2 different possible factorizations for A, and for C, you also sort of had 2 potential different factorizations. And so you're going to have to do combinations, or you'll have to try to do all the combinations of 1 and 8 with this factorization, 1 and 8 with this factorization, but then you'll do it again with 2 and 4, and 2 and 4 for this one. So you kind of have to multiply these together. You sort of have, you have 2 combinations here, and then another 2, so it's 2 times 2, right? So essentially what we're getting is we're getting the factorizations of A multiplied by the factorizations of C. Okay, this is going to give us sort of the number of combinations. But then what did we do? Well, we took these and we flipped them. So we doubled. That's a duplication. So we have to multiply by 2 again, and this is for the flipping. Okay, when you flip them, you're going to duplicate them. And then, well, we duplicated again because we had to negate everything, right? We had to put the negative sign on the other option. This gives us another set of combinations. And so this could potentially duplicate all the combinations yet again. All right. Now, if you don't have a negative value for C, you're not going to have to worry about that, right? But in this case, we do. And so essentially, it's sort of the factorizations of A times the factorizations of C times 2 for the flipping, and then potentially times 2 again if you have to negate them. This is going to give us essentially, we had 2 times 2 times 2 times 2, right? So 2 to the 4th power, that is going to be the 16 that we saw over here. All right, so this is how it works. You can imagine maybe you had different numbers. Maybe you had a different quadratic that we started with. How about a 12x squared plus, I don't know, something here. I don't care about that too much. And we'll do a minus 18 over here. So in this case, if you look at the factorizations here, well, for the first one, you could have 1 times 12, you could have 2 times 6, you could have 3 times 4. You got 3 different factorizations here. And for this negative 18, you could have a negative 1 times 18, a negative 2 times a 9, or a negative 3 times a 6. So that's another 3 potential factorizations. So what we would have here is 3 times 3 times 2 times 2. Well, 3 times 3 is 9. 9 times 4 is going to be 36. So we're going to get 36 potential combinations here that you would have to grind through in order to figure out what is actually going to match the middle term here, whatever that is, for your B. Okay, so that's a lot of combinations. And if these were numbers with 5 factors, right? You'd have to be grinding through like 100 combinations. It's not practical. Okay, so what we need is a better way to do this. This method works, and it's pretty good when you only have, like, these are prime numbers, right? Because then you only have one set of factorizations for each, or maybe one of them's prime and one of them's not. Then you kind of have 2 sets of factorizations and this, and then like the flipping, so you get like 4 combos. 4 combos I can work with. 16, 36, 100 combos, can't do it. All right, so there is a better way, and we're going to learn about it in our next lesson. So come back then, where we're going to learn the best way to factor quadratic expressions just like these, and I will see you there.